Okay, now that we just talked about EMF, we're going to move on and we're going to look at some ways in which we can actually kind of solve some problems using these ideas. But the first thing that I want to do now is to talk about this equation right here. This is what we're going to be using to solve some of these problems. So I'm going to drag this one back over here. I could have written this down, but it's nice the way the book... So I basically just took this from your guys' textbook. So whenever you connect a circuit, okay, so let's actually talk about a battery real quick here. What's going on, walk on? Oh, upside down. All right, so let's say that we hook up a battery right here, right? And let's say that we make it so that our battery looks something like this. You know what? I almost want to just do the problem. Whatever, we'll just start off by describing what this means. So let's say I've got a battery, right? Let's use a little dark green so it shows up a little better for you guys. Okay, so let's say we've got a battery right here. So there's our battery. This is positive. This is negative, right? What the battery is effectively composed of is you've got kind of two things that are happening inside of your battery here. The first thing you've got is your EMF source, okay? So your EMF source we're going to represent with this line right here and this line right here, with this being the positive, this being the negative, and I'm going to label that that's E for EMF, okay? Within a system like this then, and let's go back to black. There's also going to be, in any individual battery, because the battery is actually composed of parts, there's also going to be some type of internal resistance within the battery right here. We label that as little r, okay? E represents the EMF of the source. It's kind of an ideal EMF. When you go and buy a battery and it says 1.5 volts, that's kind of like the ideal EMF. If you go buy a 9-volt battery, that's the ideal EMF. In reality, between the 2 points in the battery, I gotta make sure I do this the same way your book does real quick here. I want to look at their picture. They put B on negative, right? Yeah. So they define, if you define this to be B and you define this to be A, the actual potential difference between these 2 points, when you actually go to measure it with, let's say, a voltmeter. Okay, so you guys have used voltmeters before, right? So if I, for example, connect a voltmeter here, so this symbol right here means voltmeter. If I connect a voltmeter to here, now what happens is that current is going to flow in my system. It's going to flow from positive to negative, so we're going to have current flowing like this, and then back up like this, right? It's going to flow around in the system right here. And the voltmeter, it has some resistance. Resistance, again, is the resistance to the flow of current. It's usually on the order of 10 mega ohms. Ohms is the unit for the voltmeter resistance, the resistance of the voltmeter or something like that. So now what happens is that because you actually have current that flows through your system right here, the actual terminal, okay, they call this the terminal voltage, right? Because it's, if you were to take a voltmeter and connect it to the end of your battery, what happens is that current flows through the voltmeter and it measures the potential difference between these 2 points here. And we say that the potential difference between those 2 points is given by the EMF here minus IR, okay? Why is it minus? It's minus because some of the energy from the battery gets converted into thermal energy inside of the internal resistance. Does that make sense? So that's why it's minus. You've already used up a little bit of the energy of your system with this battery right here, with the internal resistance of the battery. Does that make sense to you guys? Oops. And so we often say that there is a voltage drop across that piece. You're going to hear me use this phrase more than once, voltage drop. Every time you put something into your system, it kind of uses some of the energy, basically, right? And so there's going to be a voltage drop across that element. This is why if you connect multiple light bulbs in a system, okay? If you get a little picture. So let's say I've got a light bulb here, and let's say I have a light bulb right here that I connect into an electrical system, okay? These are really crude. Okay, but I've got a light bulb, it's shining. I've got another light bulb, it's shining, right? And I connect it up to a battery, right? You guys remember the demo we did last time? We said that if I connect light bulbs like this, then they're going to be dimmer than if we connect them in parallel. Do you guys remember that? And it's because each one of them, there's a voltage drop between these points, and there's a voltage drop between these points as well. The first one uses up a little bit of the energy, the other one uses the remaining energy that's left over. It's why we call it a voltage drop. Does that make sense to you guys? Okay, so next thing we want to do then is to look at how we can analyze a circuit, okay? And this is an example problem that I pulled from your textbook right here, and we'll just move it. I want to group together these two. Well, let me do that, probably. And we're going to kind of pull this over and solve it, and we'll talk about this picture here as well. Nope. Here, how am I going to do this? Let's see, I want to grab this one. I want to group it together with this one. I want to cut. Go up here. And for this, because that's kind of big, we may need to zoom out just a little bit. You guys can ignore all this stuff. This is just for later. As we talk about Kirchhoff's laws. So this is what we want to work on here. I want to try to solve this problem over to the left. A source in a complete circuit. We add a 4 ohm resistor to the battery in this example that we didn't talk about, forming a complete circuit. What are the voltmeter and ammeter readings in this circuit right here and now? So I'm going to draw another schematic of the circuit because that's kind of small. I don't know, do I have to? I could just make it bigger. And then just label the circuit right here. So, okay, this is a voltmeter, V is a voltmeter, A is an ammeter. What we have here is a battery that has E equal to 12 volts, so that's your ideal EMF. We might as well start writing some of this stuff up here so we can kind of use it. So E is equal to 12 volts. And it has an internal resistance that's equal to 2 ohms. And then it's connected to a resistor R that's equal to 4 ohms. And we want to calculate what the voltmeter and ammeter readings are, right? So what we're going to do to solve this is we're going to say that this voltmeter that's connected right here, right, it reads the potential difference between points A and point B, okay? But between point A and point B, there is the battery, right? So I'm going to say, use a little darker ink for this. So, okay, so in the battery, between point A and B, we can say that our potential difference is going to be equal to kind of what we had before, E minus I times little r. This voltmeter is going to read out a smaller value of voltage. This thing reads voltage than 12 volts, and it's going to be smaller by that amount. But it's also going to be reading the potential difference between these 2 points, and they have to be the same, actually, because it can only measure, it's just that you can measure the same thing in 2 different ways. Does that make sense? You can either measure it like that, or you can use this equation that we had before, which was that delta V is equal to current multiplied by resistance. So the other way to find the potential difference between these 2 points, and this is another way of saying the potential difference between A and B, by the way. This could also be written as capital I multiplied by big R. Here. And I'll stop for a second. Does that make sense to you guys? This voltmeter is either going to read IR across this dude, or it's going to read E minus IR across this guy. They have to be the same thing, though. Does that make sense? Exactly. So within a conductor, you remember within a conductor, if one point is at a certain potential and there's nothing in between, that the potential inside the conductor is constant. Electric potential inside a conductor is constant. That's one of the things we learned early on in this class, over the last few weeks. So A and A prime are at the same potential. B and B prime are at the same potential, although maybe slightly different because of the ammeter. But, yep. You guys have any questions about that? It's basically, this thing is measuring the same thing in 2 different ways. Okay? All right. So our goal here is to calculate what the voltmeter and ammeter's readings are. And I think with the equation we have here and the information that's given, what is unknown in our equation right here? I mean, this is obviously unknown. It's one of the things we're finding, right? But what else is unknown in that equation? Current, right? Now, the ammeter right here is the thing that reads the current, right? And according to our equation here, we can rearrange this and say basically E is equal to I times R plus R. And then we divide this over here, and so we end up getting that the current is equal to E over little r plus big R. And this ends up being then equal to, what is it, 12 volts divided by little r plus, so this is basically 6 ohms then, right? So 2 amps. Easy problem. And then we can go back here and find VAB with either equation we want. We'll use this one. The potential difference between A and B, this would be what the voltmeter would read, would be equal to 2 amps multiplied by the resistor 4 ohms. So 8 volts. It's 4 volts less than the ideal EMF of the battery. Does that make sense? You guys have any questions? Yeah, go ahead. Yep. You guys can see my full screen, right? Is it sharing the screen right now? Okay, so the problem was that you just didn't have the app running yet or something like that. But yeah, the recording will be up on YouTube, and I'll link it when we're done. I'll have them uploaded within a few minutes after we're done. No problem. All right, so yeah, there we go. So the next thing to do here is to talk about the energy portion of this. And I briefly talked about this last time. I'm going to go through it again, and then we'll come back and solve this right here. Let me move some of this stuff off the screen, and we'll use that to describe energy something real quick. Okay, so in terms of power and energy in an electrical circuit, let's draw this up here. So we can say that, it's a darker color. In an electrical circuit, power is basically equal to one of 3 different things. It's either current multiplied, this is power by the way. It's either current times potential difference, or if we replace delta V with I times R, we can also write it as I squared times R. And the other way we can write it is delta V squared divided by big R. That's how you calculate power with an electrical circuit. We did like some simple calculations with this last time that I was on campus. So if we look at the equation that we have for our circuit right here, right? We had this equation that said VAB was equal to E minus IR, and that no, that was little r, right? And that this was equal to capital I times big R. So since these two are equal to each other, we can do the following. We can make the following statement right here. If I write E minus I times little r minus I times big R, this is going to be equal to 0. Nimra, I'm gonna put you on mute for just a second, or well, if you can. Okay, you did it yourself. Great, thank you. Okay, so E minus IR minus IR equals 0, right? And then what we can do is this: if we multiply both sides of this equation, or just this entire side of the equation, if I multiply by the current, then what we end up getting is I times E minus I squared times little r minus capital I squared times big R equal to 0. You should be able to see that each one of these represents a power. EMF, is a type of voltage, right? So each one of these is going to represent a type of power, right? One is positive, and these two are negative, right? So it's like the power being produced here is being used up by these two pieces, yeah? The entire expression... Here, let's start with this one right here, because it's the simplest. So this term right here, it represents the power. This is the phrase that we kind of use a lot. Dissipated by the resistor. That's what that expression means. I gotta look back at the problem real quick here to look at the language they're gonna use to ask this. What we're trying to do now is find the rates of energy conversion, chemical to electrical, the energy dissipation in the battery, and then the rate of energy dissipation in the 4 ohm resistor. So the chemical to electrical energy conversion, the energy dissipation of the battery, right? All these different things. I hate the words they use, but I gotta be consistent with what they use so you guys can understand, because you'll see it in your homework as well. So this right here, current times EMF. I believe that this represents, let's use a different color. This represents the rate of chemical to electrical and then the other piece, oh no, the rate of energy before and the battery's net power output. Okay, that last part. Oh, and then there's a fourth one, energy dissipation in the battery. So that's this one. So this one right here, I squared R, is going to be here. This is going to be rate of energy dissipation in the battery. So dissipation just means the rate at which it's kind of like, it's not lost, it's just converted to heat. So this is the rate of chemical to electrical energy conversion. This is the rate of energy dissipation in the battery. And when we take both of these guys together, this whole thing represents, I don't know, can anyone tell me what it is? What would that expression represent? Okay, so those are all the pieces of what we're going to need to solve for this. Maybe we zoom out just a little bit so we can keep this all on the screen at the same time. In that expression right there, we have everything we need to solve for this last part. So it tells us that we want to calculate each of those quantities. And I just wanted to identify what they are because I know this stuff shows up in your homework. And I know the language can be kind of, yeah. Does this word dissipation make sense? Do I need to define that for you guys? Yeah, basically, yeah, it's basically what it means, yeah. Dissipation basically means, do I have to write it down? It's basically just, it means the, I mean, for you maybe, but because some people might understand because it's a weird word. I know I get a lot of questions about it. It means that is where the energy is going, okay? You have energy that comes out of the battery, and it gets consumed by the resistor, and then it gets converted into like light and heat, basically. Okay, so dissipation just means the rate at which energy is being converted into thermal energy. Okay, so now we can calculate these things, right? So it says for the circuit, we have to find the rate of energy conversion chemical to electrical. Okay, so that was this one, right? So IE is going to be equal to 2 amps multiplied by the EMF of the battery, the ideal EMF, which is 12 volts. This would be like, if the battery, 2 times 12 is 24, what's the unit for energy, for power? watts. So this is going to be this thing, right? And then we use another color. Maybe like orange. This one. We could do this one too. So if we do, is that the second one? No, energy dissipation of the battery would be this one here, okay? Use purple for that. So if I do I squared times little r, then I'm gonna get 2 amps, that's the current, squared, times the little resistance, which is, I think, 2 ohms, right? And so 4 times 2 is 8 watts, right? So we've got 24 watts would be the ideal power output of the battery. This is how much is consumed within the battery. So the battery heats up and it converts about 8 watts of that energy, right? And then next we have the rate of energy dissipation in the 4 ohm resistor. Well, that's going to be, we'll use orange for that one. This orange. That's going to be big I squared times big R. So that's again going to be 2 amps. That's our current. The current flowing through the whole system is the same, multiplied by the resistor, which is 4 ohms. And so that's 4 times 4 is 16. You'll notice they all obviously sum up to, like, this plus this is equal to 24, right? And then finally, the battery's net power output is just going to be 24 minus 8, which is 16. So the power output of the battery is going to be equal to 24 minus 8, which is 16 watts. There we go. Does that all make sense? Do you guys have any questions? Okay, so this is what I want you guys to figure out then. So you have a homework problem. I think it's the second set of lab manual problems. And it's kind of similar to this. Not exactly the same. There's some weird symbols that it uses. For example, the lab manual, I'll just tell you right now, it uses this symbol. I hate drawing this thing. It's the Greek letter Z, or Xi. And they use this for EMF for some reason. I have no idea why. Probably, I'm not even going to try to justify it. But that's what they use for EMF in the textbook. So don't get confused by that, first of all. That's in the lab manual, I should say. But this would be the question that I want you guys to think about, and I'll give you a few minutes to think about it. So, what value of big R, so suppose that R is an unknown now, okay? But let's say that the rest of the information in the problem is just as it is before, right? So we use the EMF of 12 volts, we use a resistance of 2 ohms, okay? What value of R will lead to the maximum power output from the battery, this quantity? Does that question make sense to you? Are you just going to guess? I'm not asking you to guess, sorry. I want you to take like 10 minutes and try to calculate it, is what I'm trying to say. So we'll stop the stream and then we'll resume here in like, let's say, I guess I give you 20 minutes. No, that's too long. We'll do 15. So we'll do a 10-minute break, and then when we get back, we'll do 5 minutes on this problem, okay? So we're going to be doing, ooh, you can't see that, so I'll write it down. We're going to be doing a 15-minute break, basically. We're going to start again at 3:10. So stream resumes at 3:10. And if you still have questions about this, let me know. But I'm going to step away for a second. Well, I'm not going to step away, actually. I'm just going to stop recording.